Okay. A project operator eliminates columns, and this is another one where you have to be sort of careful about set versus bag. So when you see a projection in the set semantics, you're going to remove all columns that aren't explicitly listed, but you're also going to remove all duplicates that might remain. Okay, so if I project away all columns except for the last name, then you might think I get, Bob Smith and John Smith, and I get rid of first name, I'm left with two tuples or one tuple, right? Well, in set semantics, everything must be a set, and so duplicates get removed automatically. In bag semantics, they'll both be there. And if you write this query in SQL in any commercial database, what you'll get back is two tuples, both Smiths. You'll get duplicates, and then you can explicitly ask them to be removed with a different keyword called distinct. Okay, and we'll see an example of this. All right. So fine. So as an example here is project social security number and names. We only want two columns out of all the original columns that might appear in the employee table. All right, and so here's an example of the set semantics versus bag semantics. Here's the original table with three columns, and we project onto name and salary, and so that means we get rid of SSN. Well, now we have three instances of a guy named John with three salaries. And the bag semantics would be okay with that. The set semantics would remove one instance of this duplicate. And so the question here is, which one's more efficient? Well, removing duplicates is expensive, so just leaving them in place is more efficient. And in fact, that's that's really the motivation as to why. One of the key motivations why commercial databases assume bag semantics is that on every single query where you want to choose which columns you have, having an extra step to remove duplicates is sort of wasteful. In typical applications, you may not care, or you may sort of know by domain semantics that the remaining columns are unique anyway. Okay, so you can tolerate duplicates, and so forcibly removing them just to be pure with respect to the underlying semantics of the formalism was not particularly necessary. Okay. Okay. So an operator that you won't hear much about, but I do want to mention for a couple of reasons. One is that it's useful as a reasoning tool when you're thinking about manipulating tables, and then the other one is it actually is coming up more and more often in sort of analytics applications and data science applications. It didn't come up very often in traditional relational database applications, and that's this notion of cross product. And so a cross product here is for every tuple in R1, for every combination of tuples in R1 and R2, produce a tuple in the output. And so the size of this thing is the size of R1 multiplied by the size of R2. Okay. Equals, here, I'll just do it this way. Oops, excuse me. Right? Okay. So fine. So an example where you might see this and why, sort of give you a flavor of why this is coming up more and more often is that you often want to find all pairs of objects that have some similarity condition. And while in any particular instance of this problem there might be tricks to do this more efficiently, the brute force method of just generate all possible pairs and then apply some function to determine their similarity is often used in practice. Okay. So for example, if you want to compare two images for similarity, all right, you have two faces and you're trying to see if they're the same face, and you've got a piece of code that can do this. You now need to run you have two big tables full of images, or just collections of images. Well, generating all possible pairs and applying the function is always a reasonable way to do this. Okay. All right. So these kinds of operations are coming up more and more often, and I'm pausing because I was wondering whether to sort of mention briefly some of the techniques you can do to get around this, but I don't think it's going to come through very well without a little bit more visual aid. So let me skip that for now. Okay. All right, so what does the cross product look like? Well, imagine you had a table employee with these two columns and a table dependent with these two columns, and we do a, whoops, there's a, like there, we do a cross product of employee with dependent. That's all possible combinations of employees with all possible combinations of dependents. So we know there's going to be 4 tuples in the output, and you can check to see that John is here twice, once for every instance in dependent, and so on. All right. So now let's talk about join, and I probably maybe should have put a slide in here just about join in general first. So really we're talking about join. The most common instance of join that you're going to run into, and in fact if we don't qualify it, this is what we mean, is what I'll call equijoin. And so equijoin is a join with an equality condition right here. Okay, so what does join do? Join says, for every record in R1, find me a corresponding record in R2 that satisfies some condition. And in general, especially for those of you familiar with databases, you're going to be thinking about in terms of equijoin. This would be, you know, for every course and student, find me student IDs that appear in particular courses. Okay. So joins on primary key and foreign key, if you don't mind the jargon, are instances of equijoins. They need not be, is one point I want to make. So we're not talking too much about schemas in this course. I'm more interested in teaching about the relational algebra and showing how it comes up, rather than teaching about how to design a database in the first place. And the reason for that is that, you know, you often don't have the luxury, I made this point before, we don't have the luxury of a engineered schema. You don't have time to build one. You don't have, there isn't one handed to you in the first place. There perhaps isn't even much need for one, in that you're going to get your answer to a couple of questions and then you might sort of move on to something else. So there's not really a way to amortize the cost of developing the schema in the first place, and so on. So, you know, if you've worked with databases, most of the joins you're doing are going to be along these predefined relationships that are called foreign keys, but those need not exist in order to apply a join. Okay. And then I'll point out that just as a sort of syntactic note, you can write this 2 different ways in SQL. You'll sometimes see select star from R1 join R2 on some join condition, and other times you'll just say select star from R1 comma R2 where this condition is met. Now, if I literally translated this into a brain-dead relational algebra plan, and we'll talk about sort of how to do this a little bit more mechanically in a bit, this is actually sort of saying, well, hey, look, first build the cross product of R1 and R2, right? And then filter that cross product such that this condition is met. Okay. And this one is saying, no, don't do that. Actually, you know, use the join operator rather than generating the cross product. But the optimizer, the databases, are not that stupid, right? They're smart enough to figure out that even in this case, the right way to do this is to express a join. And so in practice, there's no difference between these 2 different ways of spelling the same query. Okay. And in fact, you know, to a first approximation, 2 equivalent queries, but different syntax but same semantics in SQL, there's not going to be any difference between them. The optimizer doesn't care how you write your SQL. It's going to optimize the thing anyway. It's going to turn it into a relational algebra plan and manipulate that plan to guess the best way to evaluate that query. Okay. And so I say to a first approximation because there are such things as query hints and other ways you can sort of tell the optimizer how you'd like the query to be evaluated. We're not going to talk about that because they're rarely important. And, you know, the other thing, it's not impossible to have 2 different queries that do the same thing that the optimizer can't figure out are actually equivalent. And so it's not impossible to get 2 different plans, but typically that won't be the case. And in this example, that doesn't matter at all. Okay. join versus in the where clause. I'll tend to write queries this way if and when they come up. Okay. Fine. So that's the most common and the simplest instance of this join operator. Okay. In fact, I think I did us a disservice here by doing this on left and right. This is actually kind of a nice example. This is the SQL equivalent of writing join, and this is the relational, sort of the SQL equivalent of writing cross product followed by a selection, right? They're the same. In fact, the only reason why in the algebra, remember the algebra has a formalism, maybe you don't care so much about deriving new operators. As long as you can express the thing, it doesn't matter. There's so much work and there's so many good algorithms for implementing join that it sort of deserves its place as a specific operation. We don't want to have to write cross product followed by a select when we're actually sort of talking about efficient join algorithms. Okay.